Welcome, everyone. Thank you for coming. My name is Darren. I'm a software engineer at Google. I work on Android Things security. Today, I want to talk about our approach to security with Android Things and why we think it can make a difference. I want to give a little bit of background. If you've been to some of the other Android Things talks, you've probably already heard some of this. But in case anyone that hasn't, one of the things we're doing is we're doing a SOM architecture. SOM is a system on module. It's a little board, and it has all the core components that you need to run Android Things. So it'll have your processor, your memory, your flash, your Wi-Fi, Bluetooth, power controller, and so forth. And the idea is that we support some finite number of SOMs, a relatively few number, and then when you build a product in Android Things, you pick one of these SOMs. And the idea being that we can push updates to the SOMs, a smaller number of SOMs, and that can fan out to a much larger number of products. And we can reduce the overhead that way. So when I say SOM, that's what I mean. There's some pictures up here on the slide. The other concept that I want to introduce is developer console. And that's something that doesn't exist now, but it will exist in the coming months. And this is a place where developers can go and manage their devices. They can manage updates to their devices and so forth, and they'll have an account with the Google Android Things Developer Console. So our core strategy is to build the security features into the platform, to have them on by default, and to maintain them over time. We want Google to be running the infrastructure, to take that heavy lifting off of developers, so they don't need to have that additional cost. I'm going to talk about 5 features today that we're building into Android Things. OS hardening, updates, verified boot, hardware back keys, and attestation. And I'm going to dig into each one of these, but before I do that, I want to talk about why we think these are important. What's the actual problem that we're trying to solve? The main problem with IoT security is an economic problem. We're not seeing so much new technical problems, same old buffer overflows, same old pass reversals, the same kind of technical problems applied to IoT as we've seen in computer security historically. But historically, in computer security, there's always been a trade-off, an economic trade-off between the cost of building the security in and the risk of not building the security in. And with IoT, we're increasingly and acutely seeing a skew towards lower cost. Lower cost matters. Devices are getting cheaper and cheaper. Device makers, the companies making devices, are getting smaller and smaller. And we're seeing that skew towards lower cost instead of building in the security. That's on the device maker side. But if we flip it around, there's also an economic side for attackers. There's a cost associated with building an exploit, with building an attack, and there's also a value that they can get out of it. For some hackers, it's literally their business model. They find the exploits and they sell them on whatever market they're working in, and they have those two factors in play. So I want to talk a little bit about 3 economic factors: attack cost, attack return on investment, both of these from the perspective of an attacker, and then security cost from the perspective of a device maker. By attack cost, I really mean how much does it cost to engineer an attack, and this could be how much does it cost with money. Maybe that's pay for compute cycles or what have you. Maybe it just takes a lot of time, and that's a cost too. Sometimes it also just costs skill, and sometimes skills aren't readily available. Maybe our attacker has access to a skill, or has the skill themselves. Maybe they don't. And there's also a component of grit, and that is how much frustration is an attacker going to have to go through to build a particular attack. How much patience are they going to have? And if we can sweep up all the low-hanging fruit, where an attacker is going to have to put a lot more effort, a lot more patience into finding an exploit, we've raised the bar on attack cost. And we want to raise the bar on all of these categories. The second thing is attack return on investment. Once attack is developed, how much is it worth? What does it actually get the attacker? Maybe they want to use it themselves. Maybe they want to sell it. But ultimately, what is it worth? And I've listed 3 things that make an attack valuable. One is whether an attack is pervasive. That is, whether it scales to a large number of devices. And let me give you 2 examples. Let's consider an attack that requires Wi-Fi injection. So to execute the attack, you have all your radio equipment in the van. You pull up the van outside your target, and you execute the attack, and you drive off. It might be a really effective attack, but it only scales with the number of hackers in vans, right? And so there's a real limit to what you can do with that. On the other hand, a second example, you find a default credential on the internet, you find a vulnerability where you can get into a certain type of device, and you can get into any model built on that sort of category. And you can just, from the comfort of your sofa, scan around looking for these devices and start adding hundreds and thousands of devices to your botnet. That's a much more pervasive attack. The second thing that can make an attack valuable is whether it gives the attacker some kind of privilege. So if they get execution on a device, what can they do? Do they have access to valuable data? Do they have access to valuable operations? Right? Maybe they want to control an actuator, right? Maybe they want raw access to that hardware, right? Maybe they want to take cryptographic keys and exfiltrate them, copy them off, and use them somewhere else. The third thing that I have is persistent. An attack is persistent when an attacker can stay in control of a device for a long period of time. So can the attack survive reboots, right? Can the attack survive updates? Can the attack survive factory resets, which is the ultimate persistence, right? And so if an attack is all 3 of these, pervasive, privileged, and persistent, you can get really high return on investment for that attack. Let's flip it around and talk about security cost. How much does it cost to build the defenses, and how much does it cost to build the security features into a product? And a lot of the costs are associated with maintenance and ongoing costs. So there's definitely cost of building in security features up front, but there's an even more important cost built in to maintaining it going forward. And not every company has the resources to build and or maintain these security features. And even large companies often don't have the resources allocated to do this. So for the Android Things ecosystem of devices, this is the effect that we want to have on these economic factors. We want to push attack costs up, like I was mentioning. We want to raise the bar. We want to push attack return on investment down. So for a particular exploit, there's just less than an attacker can do with that, and it offers less value. We also want to push security costs down. So for device makers like you all, a lot of the costs get taken care of by the platform, and so you just don't have to worry about them. The first feature I want to talk about is OS hardening. Hardening, in general, is improving security by reducing attack surface. And for an operating system, that means that programs that it's running operate under the principle of least privilege. It means that if they don't need a privilege to do something, then they don't have that privilege. And so if an attacker gets execution in the context of that application, for example, then they're limited to the set of things that application is already allowed to do. So there's a lot of examples of hardening that we do in Android. And because Android Things is Android, all of that hardening work just translates into Android Things. When you build a device on Android Things, you get all of that built into your device. So we have permissions. We don't do runtime permissions. We don't expect users to be interacting with these devices, but we do install time permissions, and it's declarative in the sense that when you build your application, you're going to be declaring the permissions that you want that application to have. And even though the user doesn't approve that, it's still useful, because if an attacker does get execution in the context of your application, they're going to be limited by the permissions that you've declared. The application sandbox is the same. Every application is going to run as its own UID. All the mandatory access controls that we enforce with SE Linux are going to be there. All the kernel syscall filtering that we put in. By the way, who's ever tried this? Anyone tried to roll their own mandatory access controls? Anybody tried to use SE Linux or written their own seccomp BPF syscall filters? I see a few hands, and you probably understand the pain. This is really, really hard to do. And a lot of projects start out with good intentions. They're going to build this in, and they get farther along, and they need to ship the product, and they can't get this working properly or reliably, and they turn it off. And with Android things, we get all of this working, and you get all of that built right into your platform. So there's many other things, and all the stuff, all the ongoing work that's done for Android comes into Android things. ASLR, Fortify Source. There's a good blog post on Fortify Source in Android. Check that out. Just last month, I think. Stack Protector is strong for your stack canaries and so forth. So what do user developers need to do to enable this in your platform? Almost nothing. Really, it's just the permissions that apply to your applications. And then, like I was saying, declare them only as you need them. There's another thing that you can do is if you do have something that's a very powerful permission that you do need. For example, if you're writing an Android things user driver and it has access to a bus, you may want to split that out. Split out that privileged code into a second application and just give the code that actually needs that privilege, and the rest of your code will run without that privilege. So OS hardening really goes after attack cost. It really puts hurdles and barriers in the way. It just makes it more and more difficult for an attacker to get onto a device and escalate from there. So more difficult to move from the context of one app to another, move to the context of root, move to the context of kernel, and there's this barrier after barrier, and that really drives up the attack cost. It also, on the right, lowers the security cost because for developers, because Google's taking care of this. They're doing the heavy lifting for the hardening. The next feature I want to talk about is updates. This is a pretty important one. It gets talked about a lot in the context of IoT security. And it's also pretty hard to do. With Android things, we're building in updates, and updates are going to be from Google. Every Android things device will be able to get updates from Google. So developers don't need to run any update infrastructure. We'll serve all the updates. We'll build all the updates. And like I was mentioning, with the SOM architecture, this is what really allows us to scale. So we can build for a finite number of SOMs and then scale that out to all the products that you want to build on those. It works a little bit like this. So a developer would upload their app to their account on the developer console. Right? Google has the OS built for their SOM. Right? This all gets packaged together as an update, and then it goes OTA to the device. So users don't install apps on their IoT devices. Developers package the apps that they want for their product, and that goes in an OTA update to devices. Updates are automatic. We don't want any friction. Especially when we're fixing a security vulnerability, we want that update to go out to all the devices that are active and online. And as soon as you put any kind of friction in there, then it gets neglected. People aren't sure what to do with it. And so for users, at least, there's not going to be any friction. Devices will just update themselves. They'll automatically download. They'll automatically apply the update. And they'll automatically do the restart. And we use the AB updates, right? So there's actually a robustness built in. We'll have a second copy, and then we'll boot to that. If there's a problem with it, if it doesn't boot, we'll flip back and go back to where it was before, and we can fix it from there. Updates are going to be regular. So Android has their monthly cadence for security updates, and they do this for Nexus Pixel devices, and we're going to be following that same monthly cadence. So, but as a developer, when you're writing applications, the application portion of your device, you're not constrained by this cadence. If you want to ship an update mid-month, you can go ahead and ship that update. If you want to wait till we ship the OS update, that's either way. You're not constrained by this cadence, but this will be the update cadence for the operating system. It's also worth noting that we do a lot of looking for vulnerabilities, and updates have real value when you're actually fixing those vulnerabilities. And if you're not looking for them, and you just don't know how secure it is. And so if you have an update system, but you're not looking for vulnerabilities, it really has limited value. And with Android, you get all the resources that go into looking for vulnerabilities for Android. We get that translating into Android things, and we get those fixes. So some of you may be thinking, I'm not sure if I want Google to be automatically shipping downloading and rebooting my devices and updating this thing. And there's going to be some controls. So the first one is developer controls. So every time we get an update, we're not just going to push it down to your device. There's going to be no friction for users, but there is a little bit for developers, and they're going to get a chance to test their devices. They're going to say, yes, this seems to work, and they're going to be able to push. So when they get notification, there's a new version of the OS available for their device. There's 3 actions that they can take. The first action is they can push it, and that is if they do testing, everything seems to work, they can push it, and then the update system will start pushing it out to their fleet of devices. The other thing that they can do is block it. And this is what you would do if something's wrong. If you test it, something's broken, and you can say, whoa, don't push that update to any of my devices. And at that point, we're going to want that feedback via the developer console. We're going to want bugs filed. We need to figure out what's going on because that shouldn't happen. And the third option is developers can ignore it. This may happen if a developer abandons a product. This may happen, maybe a company goes belly up or what have you. And in this case, the default is going to be to push. There's going to be a time window, and if we see no activity from a developer, the default is going to be to push the security fixes to those devices. And so potentially, that abandoned device could still be getting security fixes from Google. There's also on-device controls, because not every time is a convenient time to be rebooting or a convenient time to be doing a download. And maybe your device is a drone and it's flying, and rebooting would be bad, right? Maybe a user is actively using the device, and you don't want any jank in the experience, right? So the device controls, basically, there's going to be an API, and your application will be able to say, I'm doing something critical right now, hold off on any updates. And so then it'll be up to developers to actually have a sense for when their device when is a good time to update. So if you were to label light switches like my kids use them around the house, it would look a little bit like this. And I don't know if anyone else has kids that leave lights on around the house, but this is basically the same interpretation we want for developers when they're keeping their devices up to date. Just leave the lights on. Just keep those updates rolling for your products. And really, that's the only developer action we have for updates. Just don't block them. The real economic impact here is that return on investment for attacks is lowered. And that's because every time we're fixing vulnerabilities, any exploits that were built on top of the vulnerabilities are no longer useful. We can fix up the whole fleet of devices, and that exploit has lost all of its value. Possibly, if the exploit didn't get deep enough into the device to actually prevent updates, the update may actually clean up devices that were infected. It also lowers security costs, once again, because Google's doing the heavy lifting on the infrastructure, serving all the updates, building all the images, and also doing heavy lifting on the device with robustly updating devices and figuring out how to do that in the best possible way. The next feature I want to talk about is verified boot. We're building verified boot into every Android Things device. And some of you probably know what verified boot is. Let me describe it really quickly. It's basically using cryptographic signatures to verify code before it gets executed. So it would start on the hardware. The hardware would load the first level bootloader and check a signature on it. If it's authorized, then that bootloader would execute. It would load the next bootloader, the kernel, or whatever's next, and check the signature on that, and then execute that, and so forth until the entire OS is booted up. And what you get in the end is assurance that nobody's modified this code. This code has been authorized by you, the developer, and by Google. So again, Google does the heavy lifting. The developer console will take care of making sure all your images are signed. Google manages the signing keys, take care of proper key rotation, take care of proper protection for root keys. If there's a public key that's fused into the device, making sure that private key is sufficiently protected. And on the device, also taking some of that heavy lifting, where we have a verified boot reference code that does the actual verification on the device. And this will be running in bootloaders, and this is required on every Android Things device. The bootloaders need to be running this reference code. So I put the link there. You can go take a look at it. There's that initial step is going to be, for every SOM, is going to be hardware specific, so the transition from hardware to the initial bootloader and so forth. But once the bootloader executes the AVB code, then it's Google's signing mechanism and Google's verification code that takes over at that point. There's going to be per product keys. So you don't want some other product that's built on the same SOM to be able to run your software images and vice versa. And so we're going to be your keys will be associated with your developer console account, and only your products will be able to run your software images, and other products, it simply just won't boot. There's going to be a product ID that gets fused into the device, so it'll be a permanent association with that product once it gets locked down. We're also building rollback protection into verified boot on every device. So a rollback attack is when an attacker takes a device and moves it back to a previously authorized but vulnerable state. So suppose you have version 1 of your software, you sign it, you push it to your fleet of devices, everything's fine for a while, and you discover you have a vulnerability, and you want to fix it. And so you fix it in version 2, you update all your devices to version 2. The rollback attack would be the attacker takes the device, flashes it back to version 1, reboots, signatures check out OK, and then they exploit that known vulnerability. Right? And so what we want to happen is once it moves to version 2, it refuses to boot anything previous to that. And so we enforce that for software images. We also enforce that for signing keys. I mentioned we'll do the automated key rotations. Once a device sees a newer key, it will no longer trust an older key. The verified boot hash is something that we're building into Android things, and this is new that we're doing. And this is tied in with the verified boot system in the sense that at every stage in the boot, whatever it is that's being verified, whether it's a bootloader or whether it's a kernel image, the hash of that gets mixed into the cryptographic hash. And at the end of the boot process, you have a value that represents the exact software that's running on that system. So, and if you can remotely verify that value, then you can tell, not only did this device, when it booted, did it run signed code, but I know exactly which signed code that it ran, which can be valuable, especially when you're monitoring devices remotely. What do developers need to do for verified boot? Really nothing at all. There's going to be a factory step to lock this down, and after that, the verified boot system's engaged, and there's no way to unengage it. Verified boot, again, lowers attack return on investment. It makes it hard to get persistence. So an exploit that might have had persistence before no longer has persistence. And so that the attacker just isn't able to get control of the device across reboots, or it's much, much more difficult. So indirectly, you could say it increases attack costs, because if persistence is what they need, they've got to work a lot harder to get it in this case. And again, Google's doing the heavy lifting for the signing, so security costs go down. And so doing the heavy lifting on both sides of the device, really, right? Doing the signing on the infrastructure and also doing the verification on the device. The next feature is hardware-backed cryptographic keys, and we're supporting this on every Android thing SOM. So this works the same way as it does on Android. It's the same keymaster hardware abstraction layer under the hood for developers when you're building your app. It's the same Keystore APIs that you could use on Android. And really, it all works the same. There's one thing that I wanted to mention, that we're not doing full disk encryption. We're not expecting Android things devices to support that. And the reason is because we're not expecting devices to be attended. We're expecting them to run unattended, and they're expecting them to reboot automatically as part of these updates. And if you do full disk encryption and you don't do some kind of PIN or password or some kind of credential when you boot the device, you really lose almost all of the value of that full disk encryption. And we don't want to support a feature when we really can't get a lot out of it. So, but instead, if you feel you have sensitive data, you do want to encrypt it when you store it to the flash, you can just take a hardware-backed key, encrypt it using the Keystore APIs, and you get not only a similar effect, you get a better effect because that key is actually also associated with that particular application. So for developers, all you need to do is use that Android Keystore Keystore type provider. I put a link into the existing article on how to use Keystore if you haven't done that. But all the documentation is already there on developer.android.com. Again, hardware backed keys lowers return on investment. It takes something that's valuable, these cryptographic keys, and it moves it somewhere where it's even more protected and puts additional barriers in front of it, hardware-controlled barriers. And again, because Google and our partners are supporting this in all the devices, the security cost goes down for developers. They can just call the APIs and rest assured that everything's going to work. The last feature I want to talk about is attestation. Attestation is a bit like authentication for devices. A human might authenticate with a password, with something they know, or with a biometric, something that is part of them. But devices authenticate with something that was given to them in the factory, something where they can prove that they are authentic in some way. And that sort of cryptographic proof is we call it an attestation. So for Android things, we're supporting this for any devices. It will be optional. You don't have to key your devices in the factory, but we will support it for everyone that wants to. And a device will be able to attest that they are an authentic Android things device. They'll be able to attest that they're an authentic instance of a particular product. So this is bound to that same product ID that said that your verified boot system boots up with. So those are tied together. It can attest to a device identity, so it can prove that it's a particular device. And so if the system is integrating with a device and they see that same device twice, they know that's the same device. It can attest to its identity. It can also attest to its state. So in particular, the verified boot state is interesting, where it can actually give a cryptographic statement that the verified boot system is engaged. And potentially, like the verified boot hash I mentioned, it can give a cryptographic statement of the exact code that it booted with the last time it booted. Attestation is also tied to cryptographic keys. So effectively, the statement is that this particular key is protected by hardware that has these attributes. It's that kind of a statement. And so you can also make statements about that key, statements like, and this key expires in 48 hours, or this key is only allowed to be used in these particular signing modes, and things like that. So you can attest to those kind of attributes as well. For the attestation, the certificate authority is going to be operated by Google. Again, Google is doing the heavy lifting, doing the key management, issuing key bundles for products, and Google is providing that authority. Just doing the factory provisioning, though, of these credentials can be a real challenge in and of itself. And we also want to help there. So we're providing a factory appliance, and this will help get keys safely from Google to your factory partner and safely into the device, and really help with the management of those keys, the auditing of that process, and all of that. So the basic flow would look like if you're already working with a factory partner who has one of these appliances, you would get the identifier for that appliance. You go to your developer console, you say, I want a key bundle for this particular product. You'd have to enter that appliance ID. You download that bundle, and that bundle would be encrypted, and it can only be decrypted by that particular appliance that you identified. And so then you send that bundle off to your factory partner, and they know how to take care of it from there. So again, I mentioned it was optional, and it is, but there is going to be some cases where if you're integrating with certain applications, or if you're integrating with Cast or with Assistant, those keys are going to be mandatory, just because you need to work in that ecosystem. The last thing that we're supporting is anonymous attestation. I don't know if anyone's familiar with direct anonymous attestation. It's a cryptographic mechanism that is a little bit like asymmetric cryptography. You're familiar with that, where you have a public key and a private key. But in this case, you have a public key and you have a set of private keys, and they're all bound to that same public key. And so what happens is when you verify a signature, there's no way to tell which private key it was. So you get this attestation of group membership. You don't you don't get a side effect of identity. And sometimes this can work really well. If you need to do some kind of attestation in an ecosystem where they don't need the exact identity, then it's nice not to pass that along when it's not needed. You can do an anonymous attestation. So this would be really good in some cases where you want to keep that privacy. But there's also cases where you want that identity. For example, if you're a large enterprise, you're managing a large fleet of IoT devices. You're monitoring them. You want to know exactly which device is which, and you want that attestation of identity if you can get it, right? And so we want to support that flexibility, and so we're supporting both mechanisms. I put a little bit of code up. I don't know if anyone's actually ever coded with this kind of thing in Android. There's basically one method that you need to put on your key pair generator. So all of this slide is pretty standard code, except for that set attestation challenge method in the middle. And that's what really tells the system you want an attestation certificate chain for this key, and it'll issue one if you give it a non-null attestation challenge. So that challenge value can be anything. Here I just have an empty byte array, but this challenge value will go into the certificate. So if you want to bind it with some other system that you want to integrate with, there could be something really valuable that you can put into that challenge, valuable as a binding token. And then at the end, when you get the certificate chain for that key, that's going to be a full certificate chain that'll root up to the Google Attestation CA. There's one more thing I wanted to remind developers to do when they're working with attestation, and that is to use the key. There can be a temptation to generate this key, get the certificate chain, and then just validate that chain or send that certificate off to someone and get them to validate it. But the real value comes in when you actually use that key. When you use it, say, in a TLS client auth, or use it to connect to your VPN, or you use it to engage in some other protocol. That's when you get the real value out of the attestation. So don't forget to use the key. So attestation doesn't really make it harder to attack a device. It has more to do with how devices interact with each other and with the cloud or with other services. And again, it's really just cost that's driven down because Google's doing a lot of this heavy lifting. So quick summary. Security is built in, and we're taking care of the infrastructure. We're doing the heavy lifting on OS hardening, heavy lifting on updates, heavy lifting on verified boot, hardware-backed keys, and attestation. So that's all I have for you today. I want feedback, so please come and talk to me. I'm going to be in the office hours, which is today at 1:30 in the office hours tent, and check out our Google Plus community, g.co/IoTdev. And if you want to get started with Android things, developer.android.com/things is the right place to go.